I have to say a big thank you before everything to Manuel, to the organizers, to Professor Davila, to all of you, of course, for coming here and for spending 1 hour in the afternoon to, well, to see some talk about chemotaxis. It's maybe the N+1st talk on chemotaxis in the world, and chemotaxis is quite, well, Keller-Siegel analysis has become quite popular, I have to admit. Out of the big field of chemotaxis problems, I would like to focus on a subclass which is related to the question that you can see here. It is about primitive chemotaxis, and I will explain in a couple of minutes what I understand as primitive chemotaxis. And it is about structures. Oh, well, structures is maybe not so surprising, but what is primitive chemotaxis, and what am I aiming at when I speak about this? Well, this is the guy. Let me try to put some application framework upon all this. This is the guy that the game is about. This is Bacillus subtilis, and it is a very primitive bacterium. If you ask biologists, they say it's a very paradigm for a very stupid bacterium. It can basically only run around and eat. So this is different from this is slightly different from the kind of bacteria that Keller and Siegel in their original chemotaxis works focused on. But I will explain the difference a little later. So let us first consider this as our friend for the next minutes. And one striking series of experiments conducted with Bacillus subtilis was, well, in the framework of a sessile drop. A drop of water. You see a very big photo here of a very innocent drop, nothing else in there but water and some bacteria. And what has been done not so far away from Bath in Cambridge in 2004 was a series of experiments in the group of Raymond Goldstein. They took a photo of the droplet from the side here. You see part of the drop from the side, and you see on top you see the beginning of the experiment. On the bottom you see the end, and you see that more or less homogeneous distribution more and more becomes structured. It is not maybe a blow up in the sense of mathematics, but it is a structure of, and well, first such a stripe structure here, but then it becomes more and more complex. So it's quite an unexpected behavior, you might say, if you have a very primitive population and you don't see immediately a reason for this, why that should happen. 1 year later, they repeated this year, and you may judge yourself if you think these are more impressive, but anyway, you see structures there. But even without fluid environments, even without liquids, even without water, this Bacillus subtilis, this guy can do amazing things. You see here a typical Petri dish situation from 1990 is this experiment. You see the Petri dish viewed from above, and you see these bacteria. Again, we see the bacteria more or less radially distributed in the beginning. They form very complex sort of snowflake-like structures when they walk around and eat. This is all they do. So they walk around and eat, and they form, by the way, they form snowflake-like structures. And this is a question, of course, which is good for mathematics. How does this structure enter the game? If you browse the modeling literature, there is a lot of information and a lot of attempts to describe. If you go back to Keller and Siegel, you will also find, maybe not in the main line of the works they did, but also in some side event you find modeling on such things in a quite general framework of chemotaxis processes. But you do if you go to the literature by the people who conducted these liquid experiments, this is not so long time ago, then you see quite clearly described what is the core the core of the things that determine the behavior of Bacillus subtilis. Where chemotaxis enters is that these guys, they move, of course, they run around, but they move also, besides randomly, also in the direction of the signal, in the direction of their nutrient, which is in this case oxygen. So they move toward nutrient, and so they try to move not too stupidly. And if you try to put this into a model, then the modelers say that a reasonable approach is to consider N as the population density of these bacteria, and then you have the signal, the oxygen here, which is also measured by a continuous quantity, and you have a parabolic equation for the population density, which is, however, not a standard heat equation, as it would be if it was only diffusion, but you have this cross diffusion term here, cross diffusion because it is a second order operator, but which acts on C and not on the quantity N here. And this quantity C itself is determined by some equation that has to be discussed. In the general Keller-Siegel framework, you have some type of problem which looks like this. And let us always put this in a bounded domain with the no flux boundary conditions and with the non-negative initial data and so on. But I will explain this later. So just to make a short side comment on what is the mathematical potential of this red term here, of this cross diffusion term, let me simply go to a framework which is not, I underline already here, which is not precisely the framework that is suitable for Bacillus subtilis, because the second equation is a different one here. You see here the very classical Keller-Siegel system, which I discuss here very briefly because it is the most celebrated chemotaxis system, even though it is not the one that is suitable for Bacillus subtilis. This one has been created for bacteria which are not completely stupid, not completely primitive, because they are able to produce, and this is part of the second equation here, they are able to produce a signal. In the second equation, you see a plus N here in the end, which means that cells produce the signal, which then, of course, is not their nutrient in this framework. But just to show how dangerous this, mathematically dangerous, this cross diffusion term in the first equation is, let us briefly recall what is known for this standard Keller-Siegel system, even though it's the wrong one. You see the only non-linearity here is the cross diffusion. All the other things are linear. And this cross diffusion, this non-linearity can produce exploding solutions. This has been shown, only 22 years later, after Keller and Siegel invented the model. This may already show you that this is not a trivial thing, and only for a simplified problem, and only in space dimension 2. Jäger and Luckhaus proved in 1992 that there exist at least radially symmetric blow-up solutions. This simplification was here achieved by smuggling in a zero on the left-hand side of the second parabolic equation, which thereby becomes elliptic, and which is a very popular simplification. There is biological motivation for that. This is okay, you can do it. Of course, mathematicians, they are satisfied only if you can do the full flavor thing. But the next developments were also 9 years later only, were on the parabolic elliptic one. the extension here was toward non-radial blow-up solutions. So also there exist a lot of them. And in between, there was a proof of, well, at least one radially symmetric blow-up solution for the fully parabolic case by Herrera and Velazquez in 1996. Of course, if you want to make a judgment on this problem, you will ask, well, is this really producing a lot of blow-up solutions, or is blow-up a rare phenomenon? These parabolic elliptic results, they indicate there exist many blow-up solutions, but it is not so clear for the fully parabolic case up to this point. And also the case of space dimension 2 has not been addressed on this slide. And just to add some remarks here, I should say that there is a huge literature on chemotaxis problems. And I would say that 95% of the, I mean, if you just count pages in the literature, maybe not the quality necessarily, but if you count pages, then 95% are on boundedness results. There is a whole zoo of models which have some variations in the diffusive part, in the cross-diffusive part, in the signal production part. There are 3 or 4 or 5 equations to be added if you have some more complex couplings in biology. And there are many, many works which deal with boundedness for this and that problem under this and those conditions. But only a few really address the blow-up questions. There are interesting papers on existence of structured steady states, even bubbling phenomena. But the role in the dynamics of this Keller-Siegel system, it's quite unclear, because the standard techniques that you have, they are quite complicated to apply. There is recent developments, but this is a very, very delicate topic. Let me just say, briefly go back to the, because we want a message, go back to the question, is this all a blow-up? Is this a rare phenomenon, or is this generic? So let me just this is the last slide on the classical Keller-Siegel, I promise. Just write down something on this question. The result, namely, is that, okay, if you are willing to resort to a radially symmetric setting, then indeed you can say, with good reason, you can say that blow-up is a generic phenomenon in the 2 and higher D Keller-Siegel. And this is an attempt to formulate this in a mathematically rigorous manner, but you should not try to read all this in detail. This is just the message: blow-up is generic. And how is this spelled here? There is a set of initial data, well, admissible, say, negative, radial, or positive and radial, it's sufficiently smooth. And out of these initial data, you choose the B, you choose the blow-up enforcing initial data, which are such that the corresponding solution blows up in finite time. And this B, this blow-up enforcing set, contains an open subset in some topology, LP times H1. And well, generic means dense, and the second part is maybe the more important part. The set B is dense in the set of all admissible initial data. Of course, I cheat a little here with the topology, because the open and the dense statement, they refer to different topologies. However, this strongly says that there is a lot of initial data, especially this density statement here. There is a lot of initial data which lead to blow up in 2 or higher dimensional cases. So the conclusion at this point is that this is old already. The conclusion is that this cross diffusion term, this quadratic, well, this nonlinear cross diffusion term can produce a lot of blow up solutions. And so let us now try to describe Bacillus subtilis with that. And you will browse the bioliterature and see this is not possible. You cannot take the classical Keller-Siegel, because this guy is too primitive. It is only eating the substance, but not producing the signal. And this means that the second equation has to be a very simple one and a more substantially more, well, dissipative one, if you wish. The second equation that you see here with the red minus nc, namely, does not contain a plus n, but only a minus nc. So solutions C, the components C are a priori bounded in L infinity. This is one big obstacle for mathematicians to prove something about structure here. Just have a look at the second equation. If n is anything reasonable, you will expect that C goes to 0. Bounded domains, Neumann, 0 on the boundary, you will expect that C will go to 0. And so if C goes to 0, what can you expect? What type of interesting behavior can you expect? If C is 0 and you will believe that maybe also the gradient of C will go to 0, then the cross diffusion term will asymptotically vanish. So the rough guess is that you cannot have anything interesting here. And indeed, in the 2D case of this chemotaxis consumption system, in the 2D case, you can rigorously prove you always have blow-up prevention. Just unlike, completely opposite to the classical Keller-Siegel, you always have a global classical solution, and it approaches the spatial mean in its first and 0 in the second component. And this is quite precisely the guess. In space dimension 3, there exists a global weak solution. It is not clear yet how regular this is, whether it may blow up or not. This is not, this is not clear yet, but what is clear is that at least eventually this becomes smooth and also converges to the steady state that we see here. And of course, there is no big miracle, at least not a big miracle when developing a gas, why this should be the case here. You have just two manipulations that you can perform to the second equation and which make you believe that all this is true here. You just integrate the second equation, use Neumann boundary conditions, and you end up with an integrability property here that you see on the left, which is saying that there is some decay of some quantity here in a very weak sense as time goes to infinity, because the time integral goes from 0 to infinity here. And if you multiply the second equation by C, then you also have this Dirichlet integral vanish asymptotically in this very generalized sense. And then you have to add, and this is how the proof here works, you have to add, augment this by, or supplement this by additional regularity features, so that you can interpolate between these decay things and the higher order regularity features, which only give you bounds, but then the interpolation goes gives you decay. And this is roughly how we do it. Okay, go back to biology. This is maybe not the right model to describe neither the things that we have seen in the droplet nor that we have seen in the snowflake situation. Then you may again go to the literature. This simple system was too simple. Then you see, some papers, they suggest to logistic source terms. Maybe the plus rho times n and minus mu n squared changes the game. Or others, they suggest to add some sort of a food supported proliferation. So whenever bacteria eat, they are more likely to proliferate. But all these things lead to essentially the same result. There is convergence towards something homogeneous in the first and to 0 in the second component. Okay, what can you do? You can ask the literature again, and the literature from the group of Raymond Goldstein again says and claims that fluid interaction may be responsible for the phenomena we have seen in the droplet. And indeed, there are some impressive papers by Alexander Kiselev and Ethan Tadmore, just the very recent literature, they considered chemotaxis systems, and I underline, they prescribed a fluid. I mean, just to make a simple toy model, they constructed a particular fluid which has some effect A, B, C, or D on some chemotaxis system. For instance, blow-up prevention by some given fluid. This is what is the proof, the core of the statements here. This is not what Goldstein suggests. Goldstein suggests, but it goes into the direction, of course. Goldstein suggests to couple a Keller-Siegel consumption system to a fluid with given velocity u, so this is a new player here, via transport in the first and second equations. This is the same as in these papers by Kiselev and so on. But then Goldstein says that the fluid itself is influenced by cells. And this is the minus n grad phi in the last equation. So this is a very ugly system because it contains an unknown fluid, which has to be described by means of the Navier-Stokes equations. And this, once you have solved, I mean, of course, this is coupled, but once you have solved, it transports all the other things. This is the full model. And of course, you will say this is much too complicated. You cannot do too much because already the Navier-Stokes subsystem in the 3D case is widely, not so much understood with regard to existence theory. Of course, you know, in 2D case, it's like the Keller-Siegel consumption system alone. In the 2D case, everything is nice. The solutions are smooth. They converge to zero. I mean, without source here in the Navier-Stokes. And in the 3D case, you have, well, unique local solutions, which is not so striking, but you have global solutions. You know, since almost 100 years, you know there are global weak solutions, and they are eventually smooth, but you don't know how regular they are. And this is the open $1 million question. You have this, moreover, you have, let me do this as a side comment, you have a Leray structure theorem, which says that these global weak solutions, they are at least generically smooth, in the sense that you can find a null set of times such that outside this null set, the solution is nice and classical. And there is the standing open questions. I need not describe in detail here. There's a literature which would blow up alone a whole talk, of course, but I cannot go into details. This is all well known. And so the full system cannot be simpler than all its parts. So it is quite self-evident that you have quite a strong obstacle when you want to describe something in the end, which is qualitative. Then you have to solve the existence issues first, and so on and so on. And of course, since the invention of this model, or the proposal of the model in 2005, there was a huge activity about systems of this form. And you see here in red, people smuggled in some rates of signal absorption here, consumption, and some cross-diffusion rates in order to make it slightly simpler, because if you impose conditions, if you are allowed to impose conditions, then you always have more options to do. And this was the flavor of many of the first results here. Most of them have some handicap somewhere. They either address local solutions only, or only weak solution concepts, or impose some smallness conditions, for instance, on the initial concentration of the signal, or are such that the choices chi equal to 1 here up above, or f equal to c, they are not covered. So this is I'm speaking about 6-7 years ago. And there is a huge number of contributions, relevant, many relevant contributions to this field by many authors. Also, this has a much larger number of variants than those that you can see here. You can also find in the literature reasons why, for instance, the cell population density should have porous medium type, nonlinear diffusion, and so on and so on. So this is a literature on its own. Let us go back to the simplest one here, because we want to answer the question, is there any hope for structures? And of course, we have to answer first, is there a hope for a solution at all? Let us first go to the 2D case where both the subsystems, the chemotaxis one and the Navier-Stokes one, are not that complicated. In that case, you can dream of the full flavor result. You have always global classical solutions, and they are unique and so on. And the dream indeed becomes true. You can prove all this for this full system. And in the 3D case, the best you can hope for maybe is that you have global weak solutions, and indeed you have. There is a construction by which you can see that this is true in this full flavor problem as well. Okay, but what is the behavior now of these solutions? The behavior with regard to structures is, and this is the bad message here, this is boring again. This is unfortunately not so interesting. The 2D case, namely, is just as it was in the Keller-Siegel alone. It is convergence of the classical solutions toward semi-trivial steady states. This is the result here. But at least in the 3D case, you may hope, the 3D case is much more interesting, but no. Any weak solution in the 3D case does the same as it did in the Navier-Stokes and as it did in the chemotaxis only system. It becomes smooth eventually and satisfies this this unstructured large time behavior. And even you can prove a Leray structure theorem. You can even prove that there is no even on short time scales, there is no really substantial blow-up phenomenon. At least you have generic smoothness outside a null set of times. So this is quite disappointing at this point, even though it is quite tough. I mean, you have to work a little, and let me just try to describe in 2 slides here. Of course, it's a disappointing result, but to describe why this must be the case. Why does the solution behavior need to be this trivial? Because then maybe we can later do some step into a more promising direction. So why is this the case? So the 2 things that I discussed already in some slides before was you have these elementary relaxation properties, which you can directly obtain from the C equation. How can this be further developed? And there is, in this system, there is two miracles. These are the basics, but there are 2 miracles. And the first originates from this integral identity. You combine, will become something like an energy inequality. You combine 2 functionals. The one is this n log n integral, which is quite, well, I would say quite popular in Keller-Siegel dynamics, because you can quite well say something about the cross-diffusion interaction when computing n log n. But then it's not so standard is this gradient of the square root of c squared. So it's a directly integral, but not of c, but of square root of c. And if you combine these 2 things, you have a favorable combination. Well, this plus here, plus 2, I mean, you have a favorable cancellation in the cross diffusion part. This is precisely cancelled by the, let me go back. You don't see my arrow here, right? Can you see my arrow, my cursor?
Yes, we see.
Oh, you see, very good. Oh, this is very good. I had some experience with other presentation tools where this is not the case. If you can see so you have here the n grad c, the quadratic nonlinearity in the first equation, and here the nc in the second. And when you play this game here, then you can see precise cancellation. So this is all. Then you are always on a good track when you see precise cancellation. But there are other things in the game which make it more, well, quite ugly, I would say. The dissipative part contains some good guy here with a gradient n squared over n, but then there is this blue integral here which looks quite, well, unfavorable, I would say. It's a second order thing, but it is of log c only, and then it has a weight c which may degenerate, which may go to 0 when c is 0. So this is not, it's not so clear how to make use of it. And it was not 10 years ago, I think. And on the right-hand side, you have good things because they have a sign, at least if omega is a convex domain, which you can invest if you wish. But then there are two things coming from the fluid interaction, which evidently do not have a sign, and you need to estimate. And so you soon end up with the question, how can you make use of the blue term on the on the left-hand side in order to digest some of these red things here? And indeed, the core is the functional inequality here, which is amazingly simple because you see on the right-hand side an explicit factor in front. But it tells you that this blue thing indeed dominates something. This second order integral here, even with a bad weight, it contains some first order thing, well, also with a weight, but this is a good weight. It's not a degenerate weight. It's maybe even better than without weight. And you can play with these things in order to estimate these two things after integration by parts, estimate these two things on the right against some part of the diffusion by Young's inequality and some rest. And the rest is here. What remains thus on the right-hand side is a Dirichlet integral of the fluid velocity. And this is part of the energy inequality of the Navier, the well-known energy inequality of the Navier-Stokes system. So you add some portion, which is alpha here, you add some portion of Navier-Stokes energy, and you end up with a, well, quasi-energy feature of this form here. And then you can do what was, of course, can be done here. You can integrate and gain some regularity features, and for instance, from the dissipation rate that you see. And we are still in the first miracle. The first miracle now gives you that, well, after interpolation, you can play some standard things here with interpolation, combining this with the elementary relaxation properties. You see that the L infinity norm of C has to go to 0 first in some averaged manner here, which comes from the interpolation trick here. But then, because it is decreasing in time, because of the maximum principle, it has to decay in generic, I mean, in a clean manner, without integral. And now the second miracle enters, which will form an obstacle for all the subsequent analysis of such a chemotaxis consumption system. The second miracle, namely, says that once this signal is small, and this will become small, the C will become small, as we know now. Once it is small, it gives rise to a genuine, real energy inequality, which is of this strange form here. You differentiate a functional, which is a, well, can take p equal 2 here, so it's n squared, quite usual, but you divide by something, well, which is evidently well defined only for small c, because delta is something which is not arbitrary here. but this coupling here, this gives you a quantity which decreases, even with some dissipation here. So if C is small enough, then this guy decreases a long time, and we know that C becomes small from the last slide, and then we can exploit this thing here, for instance, for p equal to 2, to obtain after integration also further relaxation features, further decay features, and boundedness features, which can be used, for instance, in the context of the Navier-Stokes analysis. You can now control the source term, which is plus n times something in the Navier-Stokes subsystem of the whole thing, to control this thing in a sense of integral from something to infinity. And you can play all the bootstrap arguments from the parabolic and Navier-Stokes regularity theories to prove the eventual smoothness result. We know why eventual now, because eventual is only after C has become small. And then, of course, the convergence is also, not so surprising anymore. No? So these two miracles, these are they are the good guys if you want to prove something, but they are the bad guys if you want to prove structures. If you want to prove the emergence of structures, this was maybe complicated analysis, but it was not giving us what we want. So in the remaining minutes, I would not like to stop without seeing at least a little light at the end of the tunnel. I see my video has been frozen. I'm sorry. I should stop the video, but I don't. Well, I don't see the option to stop the video. Okay, then don't stop the video. I would like to show you my face, because now there is enthusiasm in my face. But just imagine you saw a face with enthusiasm. This model is still, this is again, well, what we all do when we are frustrated. We maybe question the model. If we want to describe something with the model A, and model A does not yield the result we want, then we go to model B. And this has been done a couple of years ago. I came across by meeting Ramon Plaza in Colombia. He's from Mexico, but we met in Colombia, and he told me, I have a crazy chemotaxis system. And it was this year. And I asked him, what do you want with this? He said, I want to describe structures. And then he showed me the snowflake pictures. And he explained to me that it is absolutely necessary, when you want to describe Bacillus subtilis appropriately, that it is absolutely necessary to take into account that this guy likes to move only when he has enough food. So when the food becomes scarce, then these guys slow down more and more. And this was incorporated. You can evidently you can justify it also by rigorous modeling, whatever this is, in such a way that in the first equation you have, in both these migration operators, you have a factor C. In the cross-diffusive part, from a regularity point of view, this is a nice message, because C is a bounded quantity. You can add some bounded thing as a factor to the cross-diffusion term. This does make the story not much more complicated. But when you add this as a factor to the diffusion part, and then he told me you have to do porous, otherwise you have to also take a porous medium type operator in order to have finite speed of propagation and so on. So this is a diffusion operator which is containing porous medium type diffusion, n grad n in the flux, but then also C as a factor. So this is, you may call it not only a cross diffusion problem, but also a cross degenerate parabolic problem. There is a big literature on porous medium type degeneracies, but there is not such a big literature on such cross degenerate diffusion operators. So it's a type of doubly degenerate diffusion, which is not the doubly degenerate diffusion that you usually see when the title of the paper is doubly degenerate. Doubly degenerate people usually put in the title when they speak of porous medium plus P-Laplace type, so in the same operator. But then the degeneracies, even if there are two, they both are with respect, the degeneracies are both with respect to the quantity, in that case, n, from the same equation. But here you have a C, which is a factor. It may become zero. It is, of course, it is small when C goes down. But it acts as a degeneracy in the flux operator. This is from a point of view of modeling, this is quite an interesting idea, even without cross diffusion, even without chemotaxis here. And actually also even without this plus NC, which I only introduced here, you can put it zero. I only introduced here in order to really fully copy the model that they propose. And there are precedents in the literature. This is not the first paper from 2013. There is also a paper from much earlier from Japanese guys who have this whole thing without chemotaxis. So the cross degeneracy is also contained there. So all my words should only say that this is maybe an potentially interesting new mathematical type of model. And secondly, to say that it is quite hopeless to do a comprehensive analysis here. Even already at the stage of existence theory, you have this doubly degenerate thing, and it is not so clear how to control it. And this means, for instance, that in 2D case, I have no idea whether it is possible to construct global, classical, or even standard weak solutions. There is only a very, very, very generalized concept within which, I do see something. Of course, I am not. Maybe I'm simply not strong enough for that. But at least in 1D case, let's take it as a toy. In 1D case, you can prove there exists something which deserves being weak solution, named weak solution, and which is also a bounded thing in both components. But what can we say again about structures? This is the really last point I would like to make. Still, we have problems about the second equation. These problems namely say that we have these elementary relaxation properties which are still the same. And so still the same is that C goes to zero. C goes to zero with respect even to the L infinity norm. So there is the story begins as it began 10 slides before, and of course you may expect that the end will also be the same. That also n will now go to some constant, and this is all not interesting. But the reality is different. In this 1D model, it is possible to first, it's not too surprising, to identify a limit. This is difficult, but it is not surprising. There is a limit, to which n stabilizes. Of course, C goes to zero, as I said. But what about this limit? And this is now the interesting part. This limit, this large time limit of n, is the evaluation of a solution of a parabolic porous medium type parabolic problem. So it's degenerate, but mildly degenerate, just a in a single way. And this is the evaluation at a fixed time. At a fixed finite time. So it's not a large time limit here that you need to take in this porous medium type problem. You evaluate this solution at some fixed time. And of course, you will easily guess that this will, in generic cases, not lead to anything constant for the large time limit of n. And indeed, there exists, you can explicitly prove, there exist many initial data such that this limit has a structure. It is not a blow-up thing. And the n infinity, yes, the n infinity here is a continuous bounded function in particular, but it's not constant. This is the snowflake, the 1D, of course, snowflake. But it is more drastic. This problem, this cross degeneracy has two more striking, I find, striking effects. Just have a look at the system upstairs. Just have a short browse what may be the steady states. You see C is equal 0 is a steady state. And if you insert C equal to 0 into the first equation, you see a surprise. The first equation is satisfied automatically. So whatever n is, just formally, of course, whatever n is, you have a steady state when you put 0 as C. So in part 4, it is written here that any pair n star, any function n star, with 0 is a steady state. And the message in part 4 is now, whatever you take here as n star, any structured thing, you end up with a stable equilibrium. This is not only some equilibrium, it is stable, meaning that in a mathematically rigorous sense, this is not a formal or linearized stability or whatever. This is a non-linear, rigorous result saying that whenever you have such an n star, you can find, or in any neighborhood, you remain in a neighborhood. This is a stability. And the last but not least effect of this cross degeneracy is that you may have persistent localization of solutions. So in porous medium, you know, porous medium equations have their support in the whole space. For instance, you have the Barenblatt solutions that support propagates with finite speed, but eventually it reaches any point. But this is not the case here. If you take any compactly supported initial function, just think of the snowflake situation. You have this initially compactly supported bacterial population, and then you have a small signal. You have a nutrient poor petri dish. You have almost no nutrient there. Then it happens what you see. The snowflake is a snowflake. The support of the solution will remain compactly supported inside. Omega depends on the, of course, on the L infinity norm here of the C0 for all times. So it's not only finite speed of propagation, but persistence. So, and what is the, just if I have 2 minutes, very good. Then I can give you a very rough sketch of what is the mathematics here. Well, it's again a sort of a functional inequality thing. The functional inequality here now is, however, a Harnack inequality, but it is an elliptic Harnack inequality. It means that you have an instantaneous Harnack property, quite different from those you know from parabolic equations. You know, in parabolic equations, if you want to have a Harnack inequality, you usually have to wait for a while. So you have some space-time domain within which you gather information, and then you wait a second or only half a second, but you have to wait in order to have a lower bound for what you want to bound. And this is here instantaneously. And this is a particular characteristic probably of the 1D setting. But well, it's our toy. It's okay. You have this Harnack inequality, meaning that you have a very regular type of convergence to zero in this C part. In particular, this means that, and you can prove that it is that this decay is integrably fast, and that if you now rescale the first solution component by rescaling the time with this quantity inside, then Z, this new quantity, solves this porous medium type problem that we have seen here. This porous medium type problem with this coefficient A here, which is of course a rescaled version of the C upstairs. This A is bounded not only from above but also from below by a positive constant. So it's no further degeneracy here inside, because C is bounded from above and below by its maximum and its minimum, and the minimum is bounded from, the maximum is bounded from below by the minimum, and this gives you a two-sided bound for the A. And because this solves a good porous medium type problem, this Z, it's satisfied by classical Porcio-Vespri, for instance, Hölder regularity theory. It satisfies a Hölder bound. And in particular, you can extend the solution Z up to time 1, which is originally excluded here. But of course, you have a continuous limit, and this continuous limit is then the large time limit of n. So a brief summary. The simple oxytaxis systems, the nutrient taxis systems that we have discussed in the beginning with regular diffusion, have no non-trivial asymptotics, no structural support at large timescales. Of course, it is not fully clear what happens at intermediate timescales. So especially in the 3D case, you may even have blow up, but after a while, everything becomes smooth, and in the large time limit, things are homogeneous. So the big guess is that also on small time scales, there is no dramatic structure development. It is not clear what happens if you may change the boundary conditions, and of course you can dig deeper here in order to save these models and to make them appear more appropriate. However, if you make something completely different already in the beginning of the modeling, if you insert such flux limited cross degeneracy migration mechanisms, then you of course encounter many unsolved things, many unsolved problems, questions concerning existence theory. But even in the 1D case, we have seen that there is a stability and of heterogeneous structures. There is emergence of non-trivial large time behavior, and all the things that you would see in the experiments are at least qualitatively potentially described by such problems. And I think these models are also interesting from a mathematical point of view, because degenerate parabolic equations have been studied in a really huge literature. The porous medium analysis, or the fast diffusion analysis, has really seen many deep contributions. But these cross degeneracies, they seem to bring into the game in a quite natural manner, by coming from meaningful application, seem to bring really fresh thing and fresh new questions, and absolutely non-trivial new questions into this field. And it's always good to stop with open problems, and particularly when looking at the time, I think the word stop is a very good thing for this minute. Thank you very much.